Okay, so my name is Matt Johnson. I'm a third year in Professor Green's group, and I'm the lead developer for RMG-database. Although I also have a lot of expertise in how RMG decides what species to add and how to manage what reactions it keeps and what stuff it tosses. This lecture we're going to talk about the RMG-database, which is essentially how it's structured, what's available there, how do you modify it, add new rates and new thermochemistry to calculate it. And so first we're going to start and talk a little bit about why we care, why we want to calculate these parameters in the first place to improve our mechanisms. So parameters of kinetic models. So if you consider this reaction, so A to B and B to A, to properly define this, we need to know how fast does it go in the forward direction, how fast does it go in the reverse direction. However, we have relationships that describe the relationship between these two rates, and we know the thermochemistry. And so for this reason, in RMG, we calculate the reverse rate as a function of the thermochemistry for two reasons. First is that the thermodynamic properties are easier to estimate than rates. The second is that you get better cancellation of errors overall, because this creates sort of a balancing of the stability of different species and makes sure that you reach the same equilibrium. And also that there are a lot more reactions that you would have to calculate if you just calculated the reverse reaction rather than the thermochemistry. And so this sort of, in terms of estimating what all the rates should be in a model, we have two separate problems. We need to estimate the thermochemistry, and we need to estimate the rates, or at least the forward rates for everything. So we can deconstruct the delta G of the reaction, which is the important thermodynamic parameter we need to calculate. And we know that this is related to the enthalpy of the reaction and the entropy of the reaction. And we can deconstruct those as functions of individual molecules within the reaction. And assuming ideal gas behavior, which is usually what we assume in RMG, at least for the simple reactors, we can calculate these as a function of the CP for any temperature and pressure. And what this in general implies is that we have sort of this relationship where we need to calculate the delta G of reaction as a function of all of these individual species properties. So how do we get these individual properties? So of course, obviously, the best way to do this is to have an experiment for absolutely everything, and then you have a pretty good idea. As long as it's an accurate enough experiment, you have a pretty good idea what everything is, and you don't have to worry about that. The next best way is to run quantum chemistry calculations. The problem is that both of these things take a really long time. And during an RMG run, of course, you don't have time to email an experimenter and ask them to go run an experiment. And while we're starting to look at ways to run some quantum calculations within RMG runs, in general, you don't have time to run quantum chemistry for everything. So we use some very simple methods to estimate these that are very fast. So group additivity, which is essentially based on the idea that thermochemical properties are highly linear. So one way to sort of look at this is that you can deconstruct a molecule in terms of the bond dissociation energies of all the bonds, the sum of all of those, and the sum of the energies of the individual atoms separated. And this is sort of natural within the chemistry. And so for group additivity, to just sort of simplify this sort of principle and make it easier to work with computationally, what we do is we break these bond dissociation energies and associate half of them with the atoms that are attached to them. And what this results in is that then you just associate energies with individual atoms within it and add them all up, which is mathematically is the same, works on the same principle. And while this is just done for enthalpy, it also works pretty well for entropy and for CP as well. So in order to determine what these are, we have to have a big database that has information related to, well, we know we want what contributions we want, but how do we know what this value is? And we do this by we have a gigantic tree in the database, and these contributions are estimated by descending this tree. So you might first say, well, the atom's a carbon atom. So, and then you're asking, so what? And there may be a value for this, but it's not a very good estimate for any arbitrary carbon that you pick, because any arbitrary carbon, the variance of the energies associated with any arbitrary carbon atom will be quite wide. And so you'll go down the tree and you'll find the one, well, maybe your carbon is bonded to three things, is single bonded to two things and double bonded to one thing. And so then you'll go to this one. Or maybe it's one single bonded to four things, and you'll go to this one. And then once you get to this one, you can look at there's a whole set of ones that it can move down. And eventually it will either hit something here where it doesn't have anything more specific and it will stop at that node, or it will continue down until it hits the most specific thing. And that would happen, say, in the case of this tree, say you had a C bonded to two H's, an O, and an N. Because when it hits this node, there won't be anything below it that matches it. And so it would stop there in this hypothetical tree. Our actual trees are much more complicated and have stuff all the way down here, especially for carbon. Part of the structure and how this works when you actually look in our database is that in a lot of cases, you'll go all the way down and you'll hit a node. There'll be a node there, but it won't have any data at it. And so usually what will happen instead is someone went through and they were looking through this and they needed to estimate certain properties correctly. And so what they did is they looked at that and said, well, I think that one's going to look a lot like this other group somewhere else in the tree. And so a lot of times what these will be is these will be a reference to some other part of the tree. And so what will happen, what the algorithm does is it descends down this tree, it finds that, and then it follows the references back until it hits that. And so other important thing is where these contribution values are from. And usually, so these are all based on Benson's original paper on group additivity, but they've been extended in a lot of different ways, taking data from a lot of different papers. Some of them have been derived by members of our group and added to calculate thermochemistry they particularly needed to calculate. Any questions? So the other sort of question is that if we, up here, the way we're sort of talking about this and extending this, we haven't really talked about, well, what if there isn't a hydrogen there? What if there's a radical? And when there's radicals, we have a similar tree of hydrogen bond increment corrections, which are corrections that essentially estimate what's the energy difference if you were to take this stable molecule and pluck a hydrogen off it, leaving a radical. And these HBI corrections they're much better than nothing, but they're based on semi-empirical calculations, and we haven't been able to find anything better yet. And what this sort of results in is that in general, these group additivity methods will work a lot better on stable species because these HBI corrections aren't based on high-level calculations. But they work reasonably well for our purposes, although all of the important radicals are particularly important to calculate at higher level or get experiments for. Okay, so now I'm going to pull out the database, and so this is what our general thermo tree looks like. So here you can see is the most general atom that you can associate stuff with. It's a single R with no radical electrons. And you can kind of go through here. So here's an example of one that's referenced to another node, where here we've got a C double bonded to an O, with the O, and the thermo is referenced to the label of a different node rather than a piece of data. Whereas here, down here in this one, it's referenced directly to data derived from some calculations here. And in particular, if you're working with a particular molecule and you're interested in you have a particular functional group or structure on your molecule, in general, you can go into our, when you run RMG, there will be, I'll talk about this later in the next lecture, but inside the output mechanism, for each species, it will have what all the groups are that contribute to your thermo. And so from that, you can go into here and find that and search for that in here, find that specific thermo node and see if it's a very good one, or where the data is actually coming from, which tells you whether it's a good estimate or a bad estimate or not. And if the thermo's none, I believe it goes up a node. It goes one node. Okay. Any questions about group additivity, thermo? Nothing? Okay. So now we're going to talk a little bit about neural networks, which is our much newer way of estimating thermodynamic properties. So a neural network is really, so if you know about linear regression, where you essentially have a bunch of a times x1 plus b times x2 plus c times x3, and then you adjust a, b, and c just to get the right values. And there's a lot of nice mathematical ways for dealing with that. A neural network is essentially composing a bunch of those together and then adding a little tiny nonlinearity at each level. And the reason they do this is because a lot of the standard, when you normally just do a linear regression, it's very sensitive to what specific things you chose as your inputs of the regression, what sort of variables you picked. And which are called features. And what neural networks instead do is they have a bunch of layers of this that have a little, that work like this. So it's essentially you have a matrix here times your input, and then you add some sort of bias, and then you apply some function that's slightly nonlinear to it. And if by fitting to this sort of framework, what you get is you're able to slightly modify what the features are in order to get better features in each layer. And by training this net, eventually what you'll be able to get is an output that is much better than you would be able to get by a standard regression technique. The most important aspect of this to understand is just that a neural net is slightly nonlinear, and it uses that slight nonlinearity to determine what's important within the model and filter it out over a course to get a output value. So one of the technique developed by Kei Hong in our group is this molecular convolution algorithm, which is a fancy way of saying that it treats locally identical structures within the molecule the same way, regardless of where they're located within the molecule, which is something that makes sense. It makes sense, and it's sort of the way it should be. But what this essentially does is it drastically reduces the number of parameters in the neural net that you have to care about. And by treating all of those, reduce the weights, and essentially this is sort of makes it easier to train, and they're able to. So we're also able to estimate uncertainty in these models. And the way we estimate uncertainty is we have all these set of linear regression, linear operation of matrix times a vector nodes with the neural net. And what we do is we randomly turn off half of the nodes each training step. And what this does is essentially means that the neural net has to kind of adapt to the fact that maybe it needed this node really bad, and so it'll develop this node so it does what that node does. And what that really does is it makes it so that instead of having one neural net, we have a bunch of different neural nets embedded in our neural net that we could just generate by just randomly picking nodes out of the neural net. And what's really nice about that is that all of these neural nets have slightly different predictions because they've been trained to match the data, but outside of the data, they can go off and do whatever they want, as you can see here. And because of this, we can use this to estimate the uncertainty in the neural network predictions, because we can estimate the uncertainty in the models by sampling a set of neural nets from our overall neural net by picking different nodes. So in general, how this works is we train it by stochastic gradient descent, which generates a big giant file full of neural net weights, and from these weights can be used to make these predictions and estimate the uncertainties. So the neural net in general, sort of the summary, this is absolutely the most important part on the neural net, the most important part to understand, which is that the neural net works really well on unfused polycyclics, fused polycyclics. It's also a bit better than group additivity on nitrogen species, and for really oxygenated stuff, it's not too bad either. But for other species, currently group additivity is better, primarily because we haven't trained the neural, we don't have a lot of the data that Benson was trained on. We haven't gotten around to compiling it all together and training it on the full set of data yet. So right now, it's important to sort of, if you don't care that much about these applications at the moment, it may be better to just use group additivity. If you care about some of these, we have a lot of settings that let you change what stuff's estimated by the machine, the neural net, what stuff's estimated by group additivity. Any questions on the neural net?
Can you go back a couple slides? Yeah, that one. So that one on the lower right, I think should illustrate the point that when you're a region where there's not enough data to tell the neural net what's really going to happen, and the neural net's just making like an extrapolation, it could be all over the place, and it could be even much worse than what's shown there by the spread of colors, because really maybe the real curve goes straight up right at the end there. Who knows? And so I think that it's not so reliable to read the uncertainty from the difference of the different neural nets, but instead, where there's region where they disagree a lot, that should be a region where it's telling you, watch out, you can't believe it. And so that's where you need to get some more data if you really need to know the value there. Whereas other cases where they do agree pretty closely, usually it's pretty reliable that they're all pretty good in that region.
That's why we have a couple questions from the chat. The first is, go back to the HBI correction slide. What is HBI correction? Why do we need it for radicals compared to group additivity? So group additivity, or at least our formulation of it, and I think most formulations of it, are primarily focused on predicting the properties of stable species. And so in order to move, and so a lot of if you can predict a stable species really, really well, then you can sort of start looking at, basically the idea being that it was easier to predict the stable species if you already know what the actual species, you have a value for this, or sorry, it's easier to predict the radical species if you know what the value of the stable species is. And so what actually RMG can do is also, if it doesn't have to just do this off group additivity, it can also do this off a library value. If you have some CBSQB3 calculation for the stable species, it can do this for the radicals. It can do this to estimate the value for the radical species. The hydrogen bond increment method is really useful because it enables us to convert stable thermo to radical thermo. And if you wanted to build a group additivity method that worked for every single radical, that would be a lot more complicated. You need a lot more calculations. I'll check. And the second question pertains to the neural net. We might need some clarification on this, but what type of sampling is used in the neural net? Is it random sampling?
For Dropout?
I'm not certain. I'll ask for clarification.
Okay.
I'm a little bit confused by the question as well.
If it's for Dropout, I think it's random, isn't it?
Yeah.
Yeah, they randomly turn off.
And then also sometimes they randomly choose molecules out to separate from a test set and a training set.
Yep.
That's usually done that way, though it doesn't have to be.
How are you optimizing the topology of the neural net?
It's stochastic gradient descent.
The weights or for the topology itself?
Oh, for the weight.
How are you optimizing the topology?
So it's in this one I think they locked it, but in some of our work there's like heuristics to say like how many nodes there are at each level and how many depth and all kinds of stuff, and those are like done as outside optimization where those control variables are also optimized as well. But you need to have quite a lot of training data to make much sense out of that. But we have a few cases where we've done that.
Mark, did you hear anything back?
Yeah, it was for the dropout, for the random sampling.
Okay.
So I think we're good.
Okay, we're good? Okay. Okay, so now we're going to turn around and talk a little bit about rates. So estimating the forward rate for a reaction. So obviously, as with everything else, the best way is an accurate experiment. The next best way is quantum chemistry. But it's important to know that it's a lot more tricky to do quantum chemistry for rates than it is to do quantum chemistry for thermo, because you have to find the transition state. There are a whole bunch of issues related with that. But those are long ways, and a lot of the time these ones require human intervention too. And so we need fast ways. So unlike so KF has a nonlinear relationship, unlike thermo, which is there are nonlinearities within thermo, but they're nowhere near as strong as they are for rates. And there are a lot more special cases in thermal estimation, and also we'd like to get the exact answer if it's present in our database. And so we have, what RMG implements is a set of rate trees, where the idea is, so we structure our rate information within isomorphic trees, which is essentially, we have some overall formula for the reaction and how it can, okay, that was we have some overall formula for the reaction. So in this case, what we have is we have this double bonded structure with a radical adding to it, which gives us our addition multiple bonds. And what we're saying here is we're saying that anything double bonded to some other thing plus some other thing that's a radical can do this reaction. And then what we do is we separate it and we break this apart. So we have the double bonded thing and we have the radical thing, and then we make these trees off it, all the sorts of things that these can be. So in this case, we say one of the R's is it could be any of these things, and then we can look at this specific one, C double bonded to R, and look at these individual possibilities. And if we pick this one, we can get more and more specific. And so we have this recipe associated with the trees, and each tree describes an independent section of the original recipe. And then also it is that we keep this subgraph isomorphic. So each node here should match the node above it. It's important to note that just because we've built the tree and the tree extends out this far doesn't necessarily mean that there's data at all at these points. Currently, all of these trees were generated manually, where someone sat down and wrote out all the substructures to build these trees in the database, and then they just added a bunch of rules and stuff that went in the database. So usually, let's see. So when we actually sort of estimate within the rate tree, is we descend here, and so say maybe we follow this all the way down to here, maybe this down to here, and we're looking at and once we're at a coordinate in the tree in a certain sense. We're down here and we're down here, and you can sort of think about moving away from these points. So moving up might be one step from here, and moving up here might be one step in this dimension. And so what we can think about is, if we suppose there's data at this point in the tree, which means that there's a training reaction that is exactly hydrogen and this structure, then we'll have a training reaction here and it will use that training reaction. But we might not have a training reaction there. And so in that case, we may have to move up. So maybe there's one here at H here and C here. And in that case, we would move up here and we would stay in the same place here. And that would give us one movement here and no movement here would give us a movement of 1 in Euclidean space for this, which is a value that you'll get when you run the RMG job. It'll tell you how far away you were. If it estimates it from something that's far away, it will tell you how far away it was, which is a measure of how good that rate estimate is. However, there's also another question here. So what you can also get is average rate rules, which is, so suppose there's one up here, but there's also one up here and this one. And in that case, they're both 1 Euclidean distance. And so what RMG will do is RMG doesn't know which one's better, and so it averages the two of them together and uses that value, which will give you an average rate rule. Any questions? This is one of the more complicated topics here.
Yeah, so in your output file, you'll see some of the rate estimates will say on the right-hand side, average of, and I'll say whatever rate rules were averaged. When you see that, that's when you should be really alarmed, because it means that RMG had no idea what it was doing, and so that rate estimate might be really crazy.
Yep. Okay. So the way it currently works right now within RMG is, so at the beginning when you start the RMG job, we load the tree in terms of the nodes and all of these substructures. without any of the data in it. And then we load our training depository separately, which is just a pile of reactions that match this reaction family. And then what we do is we take each of those and we descend it down both of these trees to the most specific point and place it at that point within the tree. And so that's what's happening when you add a reaction to the training set within RMG. What happens is then every time you run an RMG job, it loads that and descends it down the tree and puts it at the right location in the tree where it belongs. So some other things to know is that in general, bimolecular reactions have bimolecular trees, which means they have 2 trees. However, for unimolecular reactions, they usually have 3 trees. There are some exceptions to both of these because some of the reaction families, particularly, are somewhat complicated. But unimolecular trees have 3 trees because we have, well, for the bimolecular, it's obviously simply for one of the reactants and one of the other reactant. For unimolecular, we have a tree for the backbone that connects the 2 reacting groups and a tree for each of the reacting groups. Okay. So this is the hydrogen abstraction tree. And so in this case, so here we have something that isn't a hydrogen bonded to a hydrogen, and that's the hydrogen that's going to get extracted. And this is part of, perhaps it's better to show you the bottom. So at the bottom is the tree that puts all of these nodes that are above in the family file. So each of the groups defined above in this file, you can see we'll have a coordinate here. So here's the most for the X bonded to the H that's being abstracted. This is the tree for that. This is the least specific node for that. And then it goes down to the second level, the more specific nodes, and then the even more specific nodes, which are all defined up here by these little groups, and have a label that you can reason some of it out, and some of them are a little bit harder to make sense of. But all of them are defined in terms of the adjacency list, which I think Alon talked about very briefly in the last lecture. But there's also within this tree, because this is a bimolecular family. We also have the second tree here. This is the radical that's extracting the hydrogen. Any questions?
Let's hold for a few seconds just in case anybody on the chat has a question. While we're waiting, do you want to explain the adjacency lists? Because this will show like the functional groups that we kind of glossed over.
I don't feel like explaining it from the ones that aren't I prefer the ones that are the explicit carbon, not carbon double bond or whatever that. I think it's easier to explain that way. And these ones are that way. But here's our training. So here's the training live depository for H abstraction. And so here you can see that we have this reaction. We have its degeneracy, which is very important for this stuff to calculate, because the degeneracy of the reaction you're estimating may not be the same as the degeneracy of the reaction that was used. And the degeneracy is essentially, to put it in a very simple, oversimplified way, is essentially how many ways the reaction can happen within the 2 reactants. How many, in this case, I assume there are 2 hydrogens that it could pick off that will result in the same reaction. But it gets a bit more complicated than that if you go into the details of symmetry and stuff. but most of these have explanations of where the chain reaction came from. Although there are some, what's worth talking about is that in a process this last year, originally we had rules which were fixed points in the tree, and we converted them into training reactions, because it makes it a lot easier to work with and a lot easier to manipulate stuff, and also because we're trying to train estimators that aren't stuck with the tree structure we have. And so there are some of these reactions here. You can see it's converted to reaction from a rate rule, which means that we had the group structures for it, but we didn't have the explicit reaction structure. Most of these, I did a sample of it, and most of them are correct, but some of them will be the wrong reaction. And so if you're really dependent on this, you should check. It will have the source. You should check the source to be certain that it's the right reaction. Most of them should be correct, but that's something that's worth knowing. Any questions from the chat, Mark?
Not at the moment.
Okay. Oh, yeah.
Some of the reactions you have, when we go through the first step, you have like a radical and it makes it unstable and it's not at equilibrium. So how are you able to then impose a rate law when it's not at equilibrium for some of the reactions you have on there?
How can I, how do we get this?
Yeah, because like some of the reactions for the kinetics, like you have like multiple steps, transition states. So that means you don't have an equilibrium.
So all of these all of them in our training depository are elementary.
Oh, okay.
Everything in all of it. Thank you so much for asking that question, because that's actually really, really important. That every reaction in the RMG training database has to be elementary.
Okay.
Because otherwise it's all one transition. Yes.
Yeah.
That's an excellent question. Excellent question. They are all one transition state, which is actually a problem I'm going to talk about later in the next lecture, because it's related to when you add a reaction library where some of the stuff isn't elementary, you can run into some problems, because as you can imagine, we have all of the individual steps that make up that, and then someone adds a reaction like that, and we don't actually have a way to detect when that happens, and so you can end up with duplicates. Mark, anything? Any other questions on this this section with rate trees? You're good.
Okay, your mic cut out for a second, but I think we're back.
Okay.
I think we're good.
Is it back?
Yeah, I hear you.
Okay. Okay. So another thing you'll probably
Sorry, it just came in. Is there any pericyclic reaction database?
Pericyclic.
Like Diels-Alder type reactions.
Oh, yes.
So we have some of those we have, but not every one that there is.
Yeah. Okay.
Okay, we're good to go.
Okay, good. Okay, so group additivity for kinetics. So if you look at the RMG website, Max is going to talk about this, I think, tomorrow morning. And he's going to talk about the RMG website. And what you might see is when you estimate kinetics on the RMG website, it'll give you a value for group additivity kinetics. And this is indeed implemented in RMG. And it was created originally, they were trying to make a method that was better than the rate trees. But at the time, it was originally found to be less accurate than the rate trees. And while it does function properly and it provides an alternative rate estimates, we don't really have any guarantees as to its accuracy. So we would highly recommend that you not use its rates, although they may be worth looking at just if you're just to see if you're doing some sort of comparison between rates. In general, my experience with them is that they're either pretty good or totally off. And it's heavily family dependent. Primarily because it takes a lot more training reactions to train a group additivity method than it does to train a rate tree. So another thing worth spending a little bit of time talking about is that in the future, what will hopefully be implemented over the next year is that we won't actually, the trees won't be maintained manually. So I've developed an algorithm that optimizes rate trees that we're planning to implement this year that makes them significantly more accurate. In this example, we got about a factor of 20 reduction in 2-signal uncertainties. And these new trees are compiled rather than built manually. So essentially, you just call a function and it takes the pile of training reactions and uses it to construct the tree. Of course, if I was going to explain this in detail, I could probably talk for like an hour. So we only have one slide on this, but you should be aware that this is probably going to happen in the future. It'll happen in the future. We're planning to just make them and then put them on the RMG-database, but you could potentially, if you wanted to, you could compile your own. We're working out some of the intricacies and some of the difficulties in compiling these right now. But this is something that's coming and that you should be somewhat aware of, that this will be a possibility in the future. So just sort of to quickly go over libraries. So Thermo Libraries are essentially just a list of species structures that are mapped to thermo values. Quite simple. And whereas reaction libraries are worth a little bit more talking about. Yes, they are reactions, these sets of species reacting to make other sets of species. But in reaction libraries are not associated with an RMG reaction family. And so in order to deal with this, what we do is we remove all of the exact duplicate reactions to a library reaction that are in RMG. So if you have A to B in the reaction library and you have A to B in all of the A to B reactions that are generated by RMG will not happen. Will be removed because what it assumes is that it assumes that what you put in the reaction library is the total rate for that reaction. Regardless of multiple transition states and all other things. It assumes that if you're putting it in the reaction library, you think that is the right rate for that exact reaction. What's important to think about though, as I was talking about before with that question, is that if you put in some reaction A to C in a reaction library that really is a representation of a pathway, multiple transition states, RMG will not recognize that it needs to replace the pathway A to B to C. And so you'll end up with both pathways, which I think our term for it is magic reaction, because they don't have a transition state. Which is something worth considering when you're doing this, dealing with this stuff. It actually gets a bit more complicated because there are some situations where the transition state's concerted, and if you have a concerted transition state, you can result in reactions that look a lot like a sequence of RMG reactions, but actually occur in one reaction. Any questions on Thermo and Kinetics libraries before I show them? Okay. Anything from the chat?
Not yet, Elliot.
Okay. So. Clementine's library, this is one of my favorites. Primarily because it's mostly active thermochemical table data, which is really good. But in general, these entries look like this, where they're essentially you have a label to it and you have a molecular structure. So this is probably and then you have the NASA polynomial data here, and then an entry here that describes where this information came from. It's probably worth taking a little bit of a sojourn to talk about the adjacency list here. So the adjacency list is essentially how we describe molecular structures inside RMG graphically. And we treat it as a 2D graph rather than a 3D set of points, which it really is, which has there's a lot of consequences of that. But this makes it easy to generate reactions. So what we do is we define each atom as a separate node in a graph, and then these define connections and the type of connection. So what this says is that this carbon is bonded to the second atom, which is this carbon, with a single bond, and is bonded to the third atom, this oxygen, with a single bond. And what it also says is that this carbon has a radical on it. So U is unpaired electrons, P is paired electrons, and C is charge, which usually, except for certain special kinds of resonance structures, you shouldn't have charge. For some of the nitrogen and complicated nitrogen and sulfur stuff, you'll have those. We also define the multiplicity, which RMG isn't. Well, it isn't always the case. RMG always assumes that the multiplicity is the number of radicals plus one, right? Yeah, the number of radicals plus one, which is essentially tends to be an overestimate of the multiplicity. The multiplicity may be lower, but in general, in most cases, it doesn't matter that much. Any questions about the adjacency list or the thermo? Anything for the chat?
Are we at a natural 5-minute pause?
We're almost there. I'm gonna show the Kinetics library, and this lecture's done. There's one more slide after that. This is an important slide. It's the most important slide in this entire presentation. So the reaction libraries are structured a little bit differently. So they have a dictionary separate that names all the species, because you don't want to define the species over and over again. So here we have a number of species defined, and then we have the reactions defined separately. Here with their kinetics and degeneracy and what's it. And then we have, of course, since these are reaction libraries, we don't just have Arrhenius kinetics. We have some of the pressure-dependent stuff. RMG does do pressure dependence, but it does it based on the Arrhenius laws. Professor Green's going to talk about that later this week. Okay. So now the most important slide in this entire presentation. How do you know is blank accurate or not? And so there's I want to talk a little bit about what the machine learning neural net estimator is good for and what the group activity is estimated for. So use those rules of thumb. But then additionally, once you're there, how do you tell if it's accurate? So for libraries, it's sort of look at first general look at what are the sources of this library. Is it experiment? Is it high-level calculations? Does it have guesses, or is it a mechanism where it might have guesses in it, or is it also have been fitted in that paper so they aren't the actual real values? So specifically for specific to group additivity and rate trees. So for Thermo, it's sort of how specific are the nodes used? Is their data at the specific node that it reaches, or is it going through a whole bunch of references? If it's going through a whole bunch of references, that suggests it's a less accurate estimate. In kinetics, it's a bit more specific. So if the Euclidean distance is greater than 0, it often means it's not a great estimate, but you can take a look at the training reaction and see how good it actually is. If it's averaged, it's almost always a really bad estimate. And then if Euclidean distance equals 0, you also need to check it, because some of the training reactions aren't very good estimates. And there are a variety of reasons why we've had to add them. In some cases, we had to add them because otherwise there was some type of reaction that was totally unimportant and totally negligible that we need to add some estimate just to make it to make RMG estimates done properly. And in some cases, it was done a really long time ago by some student who really needed to get something done fast. But anyway, you should go and check what the actual training reaction is, and then what you should also do is check how much does the training reaction look at your reaction. Look like your reaction. In general, I think we just changed all the rank stuff, but you should, if it's CBS QB3 or couple cluster or experiment or better than that, it's usually and it looks a lot like your training reaction, you're probably in good shape. If it's an estimate, you should be worried. But sometimes you'll get the important thing to remember is sometimes you'll get the Euclidean distance equals 0, but the training reaction that's matching isn't a very good estimate of what it actually is. And that's the takeaway from that part. Okay. Any questions at all on this lecture? The last slide. Anything from the chat?
Let's give the chat like 20 seconds.
Okay.
But if not, then let's take like a
Yeah.
5-10 minutes.
Yeah.
Question.
Oh, yeah.
So, when you want to choose your libraries, your thermal libraries or reaction libraries, does it depend on the initial species you're using as a reactant, or you just choose it based on the training data?
Don't worry, we're gonna talk about that.
Okay.
That's next lecture. But in general, you do want to care about, you do kind of want to guess where your model is gonna go and what sorts of thermochemistry you want. But also for thermo in general, adding lots of thermal libraries usually doesn't hurt you. Just adding lots of data. With reaction libraries, it can hurt you a lot.
Sure.
And so you have to be extra careful with reaction libraries because, as with that issue, some of them are fitted. There are a lot of ones that are fitted and that have some that they work for the specific situation that they were designed for, but they don't work well outside of that situation, or they don't pair well with RMG stuff. So you have to be more careful with that, and I'll be talking about that more in 20 minutes, half hour or so. Yeah.
Real quick, in like 20 seconds, can you explain one more time what the Euclidean distance is with regards to the trees?
So the Euclidean distance is, you can sort of look at it as this part of the tree is one dimension and this part of the tree is another dimension. And so if we're at this point in this dimension and we're at this point in this dimension, then we can sort of make decisions about moving up. And so what we do is we measure in this movement in this dimension is how many times you moved up the tree in this tree, and the distance here is how many times you moved up in that tree. So if we move up in both of these, we moved 1, 1, and so you take the you'd be root 2 distance. If you just moved, if you stayed here and you moved up 1 in this, it would just be 0, 1 distance, and so you'd just be 1 Euclidean distance.